To train a deep neural network, we rely on backpropagation, sending a gradient backward through the layers. This math assumes that when updating one layer, preceding layers remain completely locked in place. But in practice, the algorithm unlocks and updates every single layer simultaneously. This breaks the mathematical environment. A layer adjusts its weights, expecting a specific distribution of data from the previous layer. But because that previous layer was just updated, it spits out an entirely different distribution. Every layer is reacting to inputs that are constantly changing shape. This creates a highly unstable foundation, making optimization in deep architectures incredibly difficult and slow. This phenomenon is internal covariate shift, the continuous alteration of a layer's input distribution caused by preceding layers updating. The subsequent layer tries mapping a precise decision boundary, but after every mini-batch, the incoming distribution slides away. The network constantly chases a moving target. Dealing with this constant shifting severely slows down model convergence. Historically, engineers had to combat it by agonizingly lowering learning rates and relying on extremely precise parameter initialization. Batch normalization was introduced in 2015 as an architectural intervention designed to freeze these intermediate distributions in place. By actively standardizing the activations passing between layers, batch normalization takes the chaotic, unpredictable internal environment of a deep network and locks it into a mathematically stable space. The batch normalization algorithm operates by calculating the mean and standard deviation of the inputs entering a layer, taking those measurements strictly per mini-batch. This measurement is executed on a per-feature basis. In a convolutional neural network processing image data, the algorithm doesn't evaluate individual pixels. It isolates and extracts a single feature channel across the entire batch volume to preserve spatial correlation. First, it calculates the batch mean. This formula establishes the exact mathematical center of that specific feature's distribution across the current batch. Next, it calculates the batch variance, measuring the exact spread or deviation of the data points branching outward from that central mean. With those two statistics, the algorithm executes the final normalization equation. It subtracts the batch mean and divides by the standard deviation, adding a tiny constant called epsilon for numerical stability. The resulting data points snap into a standard Gaussian distribution, centered exactly at 0 with a standard deviation of 1. This absolute standardization, often referred to as whitening in computer vision, aggressively anchors the input data. The moving target problem of covariate shift is instantly neutralized. However, taking whitened data and passing it directly into nonlinear activation functions introduces a severe architectural flaw. We can see the problem by examining how this standard normal distribution interacts with a traditional S-shaped activation function, like a sigmoid. By forcing the mean to 0 and the variance to 1, the normalized data is pushed directly into the center of the sigmoid. This central region is nearly entirely straight and linear. If all the data is trapped in the linear segment, the network completely loses its nonlinearity. This destroys the model's representational capacity to learn complex patterns. To fix this, BatNorm introduces reparametrization. For every feature, it adds two entirely new learnable parameters, gamma and beta. Gamma acts as a dynamic scale factor. It allows the network to automatically adjust its variance, spreading the data outward into the curved, saturating extremes of the activation function. Beta acts as a shift factor. The network learns to slide the distribution laterally along the axis, moving the mean to whatever position optimally serves that specific layer. The introduction of scale and shift parameters ensures that distribution stability and absolute magnitude remain decoupled. This allows the network to revert the normalization entirely if a specific layer requires those nonlinear activation patterns to represent the data. This architecture creates a notorious engineering trap. You can perfectly train a model equipped with BatchNorm, deploy it to production, and immediately watch it output absolute garbage. This failure happens because the core calculation inherently relies on pulling live statistical data from a full mini-batch. During inference, we rarely send data in large batches. We often deploy a model to evaluate a single isolated data point. calculating a valid variance on a batch size of 1 is mathematically impossible. To solve this, BatchNorm runs a hidden background process during training. While calculating live batch statistics, it simultaneously compiles an exponential moving average of the mean and variance across the entire training phase. When deploying the model, the engineer must trigger an architectural shift in the code, often by calling model.eval. This swaps the model from training mode into testing mode. In inference mode, the live calculations are disabled. That single incoming data point is evaluated entirely against the static historical running averages, and then processed by the learned gamma and beta parameters. This architectural divergence is vital. By abandoning live batch dependencies during evaluation, the network guarantees stable, deterministic outputs regardless of how many inference data points are passed in at once. In 2018, researchers tested the original hypothesis by intentionally injecting distribution noise into batch-normalized networks. They found that even with increased covariate shift, the models still converged faster than baseline architectures. This pointed to a different primary mechanism for BatchNorm success. The technical evidence points to a smoothing effect on the optimization landscape. Standardizing inputs globally represses gradient explosions and vanishing gradients. This effectively irons out the steep cliffs and sharp ravines in the loss function, converting it into a smooth, predictable gradient field. This altered topology allows for larger learning rates, which in turn reduces the total number of training epochs required for convergence. This inherent gradient stability also makes deep architectures far less fragile. The network becomes much less sensitive to poor initial random weight assignments. There is even an unintended regularization benefit. Because the statistics are calculated over randomly drawn many batches, the process injects a slight, healthy amount of mathematical noise into the activations during training, reducing generalization error. However, it is generally recommended to avoid combining BatchNorm with dropout layers. The random dropping of neural nodes creates heavy variance that severely corrupts the tracking of the running statistics. By standardizing intermediate activations, BatchNorm alters the physical topology of the optimization problem. It transforms the training of deep architectures into a predictable, stable science. Despite its massive impact, BatchNorm does have structural limitations. Relying on moving averages across batches can trigger severe instability in specific architectures, like recurrent neural networks. This has led to modern, structurally simplified alternatives, like RMS-norm, designed to eliminate batch dependence entirely. RMS-norm abandons mean subtraction and moving averages. Instead, it purely normalizes against the root mean square of the layer's own internal activations, bypassing external batch statistics altogether. Training deep neural networks with tens or hundreds of layers is an ongoing fight against internal mathematical chaos. Whether you are carefully managing the training and eval states of traditional batch normalization, or applying modern variants like RMS-norm, standardizing intermediate activations remains the definitive architectural intervention. It controls the gradients, stabilizes the math, and makes deep networks practically viable.